Okay, hopefully I can help with the discussion board this week. We got a Ferris wheel. Let's just jump to the big part of it here because you've probably already read. We're supposed to basically make a function h of t that represents the height of this Ferris wheel. And so with a lot of functions, I think it's easiest if we get some data points to help us model the function. So like we want to know what's happening at time t equals 0. Right? How high is the Ferris wheel? Because that's what h in the h of t stands for. So when t is 0, what's the height of this thing? The 6 o'clock position of the Ferris wheel is level with the loading platform. So right here, we start at 1 for height, because here's the 6 o'clock position. We're 1 meter above the ground. So at time t equals 0, when we haven't been running the Ferris wheel, we have 1 for our height. Let's find another point. For mine, it completes a full rotation every 14 minutes. So when time t equals 14, we're back at 1 for the height because it's gone all the way around and we're back to the loading, unloading position. And then same thing, another full rotation, another 14 minutes, we're back at 1. So we can use those. Maybe we can make a plot and help us see what's going on here. So it's 0, 14, 28. Let's see what's going on in between these values, like maybe halfway in between. At 7 minutes, how high are we? So here we are at time t equals 0, and since mine makes a full rotation every 14 minutes, then half of 14 minutes puts me at the top of the revolution, right? So they tell us that this thing has a diameter of 26 meters. So how high am I above the ground? Well, I'm the 1 meter to start with, plus the 26 meters tall that this thing is. So I'm 27 in height. And then same thing, halfway between 14 and 28. What is that? 34. That's 21, right? That's halfway in between. At time t equals 21, we're also at 27 for the height, because we're up here, we're halfway through a rotation, so it's the 26 of my diameter plus the 1 meter of my ground. So let's try plotting those just in a rough sketch. At 0, we're at 1. At 7, that was my next on the x-axis. At 7, I'm at 27. And I'm at 14, I'm at 1 again. And then at 21, I'm back up to the top. So this should ring a bell to a sinusoidal function. It's a function that makes a sine wave. We can model it with sine, or we might be able to model it with cosine too, okay? Because it's going up to a peak, and then it's going down, then up, and then down. So one thing I notice about this is that it doesn't start at the origin, right? Sine of x, sine of x and cosine x, before we add any numbers in, you'll probably want to remember what those two graphs look like for these types of modeling situations. Sine of x starts at the origin, goes to the peak, then back down, then up, and then back down like this. So this is almost sine, just maybe sine of x plus 1. That would shift it up 1 unit on the y-axis. So that's something to keep in mind, but at least we have a general idea of what we're going to be making here. So an amplitude of a sinusoidal function like the graph that we have here is how high or how low we go from the midline. So I'm just drawing a rough sketch of where the midline might be. Okay. We can figure out exactly what that midline is because of our data points that we gathered, right? We start at 1 on the y-axis, and then their highest point is 27. Then we're back down to 1, then 27. So midway between those two, so the average, 1 plus 27 divided by 2, midway between those two is 14. So the midline for my function is h equals 14, or it's kind of like y equals 14 on our homework. That horizontal line of y equals 14 is the middle point. And now look, if this is the correct midline, then it should have the same distance from the highest point to the lowest point of the height function. So if this is 14, then we have 13 more units to go. I think it's in feet. 13 more feet to go until we hit the highest point. Or we have 13 more feet to go before we hit the lowest point. So this is indeed the midline. It's perfectly centered between these two. And that's our amplitude. The amplitude is the distance from the midline to the peak, or the distance from the midline to the valley, to the lowest point. Okay, amplitude and midline, those go hand in hand. You got to find that middle line. What's the y value? That's right in the middle of the function. And then the amplitude is the distance from that midline to the tallest point. Should be the same as the distance from the midline to the lowest point. Now the period is just how long does it take until it starts repeating itself. Like with the function sine of x, it starts repeating itself after 2 pi. Okay, that's how many x coordinates we have to go. X in our example is t, it's time. So how much time does it take until we start repeating itself? It actually just gives it to us. 14 minutes for every full rotation. Okay, and that's a coincidence that the midline and the period are the same. Just checking all my numbers here. Okay, yep. So we're supposed to find a formula for the height function, h of t. Let me make this a little bigger. Now we got some data. We're looking at the graph a little bit. We've got some ideas for the midline. I pulled over our general form for our sinusoidal function from last week's reading for us. Because A is the amplitude, we're just going to be able to plug in our amplitude in there to construct the equation for part B. D is the midline, so we can just plug in 14 for our midline. And then B, we'll have to do a little bit of funny business, and we don't have to shift C at all. C would be used if your graph didn't start at the y-axis. Okay, like we'd use C if the function started. Actually, I think we're going to need cosine. I'm sorry. Here, 1 second. There we go. I went and grabbed the general form for cosine too. Same deal. This is our amplitude. This is our midline. But the difference is sine starts in the middle. Sine starts on the amplitude. And our graph starts at the bottom of the rotation, right? Our function goes up to, what was it, 27 for mine, then down to the bottom. Up to the top, then down to the bottom. On the y-axis, when time t equals 0, we start at the very bottom. Sine is different. Sine starts in the middle, and then it goes up to the peak, and then down to the valley, and then that's where it starts repeating itself. So that's why sine, we could actually write it as a function of sine, but it's going to be easier to write it as a function of cosine. And you might have picked that up from the readings and things like that, like the homework. You can write any cosine function as a sine function. You can write any sine function as a cosine function. Some are just easier than others. And so since our graph starts at the bottom, we're going to use cosine. And before we do that, here's the graph of cosine of x before we do any funny business. It starts at the peak of the amplitude, goes down to the bottom of the sinusoidal function, then returns to the top and makes another period. So it starts at the peak. Ours starts at the bottom. So in order to make that happen, check out the graph of negative cosine of x. I'm about to sketch here. Look, this is cosine of x, starts at the peak. So if you multiply by -1, it starts at the valley and goes to the top. Oh, and sorry, cosine of x here, I gotta fix this graph. Starts at the peak, but regular cosine of x dips into the negatives like this. So we want to start at the valley, that's why we want negative cosine of x. Just like the function that we had modeled down there, it starts at the bottom and then starts its wave. So the big takeaway here is that we need to have a negative here. That way the graph starts at the bottom of our sinusoidal function, at the bottom of like that rotation, the bottom of the Ferris wheel. We had an amplitude, and I've forgotten with all my ramblings here, amplitude for mine. If the midline's 14, the amplitude was 13. That's the distance from the midline to the top. And then B is actually a little bit tricky. B has a separate formula for the period of a trig function. Oh, sorry, I got this. The period, you might recall from last week, is 2 pi divided by B. We know our period. It's given to us in our problem. Like the period for mine is 14 minutes is when mine restarts its rotation. So I'm going to plug 14 in for my period, and I'm going to solve for B. That way I have something to plug into this. That's why I have something to plug into this function. So if I multiply B to both sides, and if I divide 14 from both sides, I'm going to get B is pi over 7. So that's what I'm plugging in for the B in my equation. You'll want to do the same with your information. This is how you calculate your period. And then minus C we're not going to do because we don't have a horizontal shift. It starts right at x equals 0, at t equals 0. And now D we said is the midline, so our midline is plus 14. And there we go, there's our equation. Okay. You could use sine. I think it'll just be harder with sine because then you're going to have some sort of horizontal shift with the letter C. There's one last thing I wanted to do before I went to the graph. In your problem it asks you to say how long is the, like mine says, how high is the person when t equals 63? Well, now that I have an equation, I can plug that in. My h of t, h of 63 I should say, and you'll want to say h of t here instead of h of y, right? I was just using the general form, but h of t equals all this stuff. So h of negative 63 for that part C, you just have to plug in the number they give you for 63 here. Plug it in for where x goes, or for where t goes, in other words. And yeah, and again, same thing here. Let me clean this up. Up here we said y equals all this stuff, and that's fine, but they wanted us to use h of t for the range and t for the domain variable. Okay, so if you plug this in your calculator, just use radians when you do the trig function. We got 63 times pi divided by 7, and then I'm going to use trig. Oh, actually, I'm going to hit radians first in my calculator, and then cosine of everything on the inside makes -1. And then -1 times -13, that should be positive 13. And 13 plus 14 gives me 27. So according to my function, we should be at the top of our rotation. And let's check to see if that makes sense with my word problem. Okay, I plugged in 63 into my function. It gave me 27 for a height. So 63 minutes Yeah, let's try. Okay, 63 minutes. So 14 minutes. Let's start at time t equals 0, and let's start doing some rotations. Mine repeats itself every 14 minutes. So here's 14 minutes. Then here's 28 minutes, because that's another revolution, so plus another 14. Then 42 minutes. Then 56 minutes. And then if I try to do another rotation, 56 plus 14 will hit me at 70 minutes. I've gone over the 63 minutes. Right? So if it's 14 minutes for a full rotation, it's 7 minutes for another rotation. So if we do that number I was saying plus 7, that hits us at 63 minutes. That puts us right at the peak. So that makes sense. The function was working. At 63 minutes, we should be at the top of the Ferris wheel based on those 14-minute rotations. So this is our function for part B. And then for part C, you're plugging in a value into the function to see if it makes sense. Oh, and I should... at 63 minutes, we said 27 for my height. Let's just make sure that checks out.